Hi, morning. Welcome to today's talk. Thanks for being here. Um, Today's talk is about extending JavaScript, and just listening to that phrase, it seems like a very slightly vague thing to say. What do we actually mean by extending a language? Uh, a programming language is something that people use, and people's use cases and you know needs evolve with time, and so does the language. So the language needs to evolve, and we'll be looking at the tools which help us to evolve a language. So in our case, it's Babel, which is a compiler quite popular for use with JavaScript. We'll begin with a few terms that we'll be seeing throughout this talk again and again, and we'll just have a look at a little bit of history to get some perspective, and we'll take a look at our tool set, which we use every day but we may not actually notice we're using, and we'll learn how to extend those tools, and along the way hopefully we'll learn some things from other languages as well. The first term that I want to talk about is elegant. So what do we mean when we say that something is elegant? And more specifically, what do we mean when we say a language is elegant? Now, when you say that code is elegant, it may mean a lot of things. So let's just define what elegant means in some loose terms. First, I'd just like to say that the term itself is quite subjective, so your definition may vary. But loosely speaking, an elegant program would be something that is easy to understand for even someone who hasn't written it, and which is not too verbose. So it's not too wordy and can be written in just a small amount of space, so to speak, and can eloquently describe something, a complex idea. And in short, something that's elegant, code which is elegant, is something that translates logic into code very clearly. And an elegant language is one that allows us to write elegant programs. The second term that I want to introduce is abstract. Now, this particular idea of abstractness is quite important in software engineering overall, because just think about it. If you had to know the details of all of the tools that you were using, then I mean, you'd go crazy just with all of the detail that you would have to know, the amount of detail in the implementation. And what you can say is that the less you know, the better you can function with, a programming environment. The earliest computers were pretty poor at both of these things. They were not very good at handling abstraction because they were huge and required knowledge, deep understanding of their working if you needed to program them. You'd usually use something like assembly language to program these things. And a need arose for more human understandable languages to come up as software grew more complex. And there were many schools of thought as to how one of these languages should look and function. And some of them were like Fortran, which modeled the bare metal more closely. They were more close to the assembly side of things, while other languages were more in tune with mathematical models, conceptual models of computation. And one such example is a language which was invented by John McCarthy, who's known as one of the founding fathers of artificial intelligence. And this language was called Lisp. There's a little feedback. So Lisp was a language which was designed to be minimal. And by minimal, I mean that it didn't have much syntactic elements in it. So for example, it had basic constructs to allow you to define data, to define procedures or functions, and to apply those procedures onto data. So in this case, you can see that we've defined a function called add, and that's being applied to a list of parameters. So you can see right away that the syntax is really minimal, and you could say elegant in many ways. It's just a list of these things that are delimited by parentheses, and all of these things that are within the parentheses could recursively be these expressions called S expressions. And actually, S expressions have been used elsewhere as well, such as the human readable format of WebAssembly. It's just a very clear way of looking at things. It has a tree-like structure, an inherent tree-like structure, because it's kind of like JSON in ways, but it's more powerful because it allows you to define both data as well as programs. So in Lisp, a data and a program are almost one and the same thing, depending on how you use it. There's a notion of quotation, so that if you quote a program, it can turn into data, and then that can be passed to another program to be evaluated. So that's very useful in places like compilation and parsing. Now, Lisp has a reputation of being quite known as an academic language or something that's quite weird, because it hasn't really taken to the mainstream, but it has a minimal design, and it's also very extensible, which is why it meets both of the things that we talked about, abstractness and elegance. Elegance because of its minimal design. So it doesn't have a lot of constructs in it, but by being minimal, it is very clear to, when you think about programming, it's very easy to use this language. But when your code starts to become more complex, its extensibility allows it to be, to have proper abstractions in place. And it also has things like first class functions and closures that we use quite a lot. The people who use JavaScript here. First class functions being functions that you can pass around, and closures are functions with environments that are passed around with them. Actually, we had a part of this explanation in last talk by Himanshu. And after Lisp was invented and all of those, a lot of developments happened, and there came a need for a way to browse the internet, and that's where the browsers started to come in. The first one being developed by Netscape, a company which doesn't exist anymore, I think, but they needed a scripting language for their browser, and this language was developed by a person called Brendan Eich, who was a co-founder of Mozilla. But at that time, he was working at Netscape, and his original idea was to base his scripting language on Lisp, more specifically a dialect of Lisp, which is a variant of Lisp called Scheme. And it had all of those ideas, minimalism and abstraction, and also things like first class functions and closures. But sadly, the management didn't have the same idea about what that language should look like. And in order to cash in on the Java craze that was in at the time, they had the language sort of rebranded, and its syntax was changed to more closely match the mainstream thing. But ideas like first class functions and closures still made it to JavaScript, and we use them every day. And there are also things like this function called eval, which allows you to take a string, and if it's valid JavaScript, parse it and execute it. So eval stands for evaluate. And that's a little similar to the idea of quotation in Lisp, where you can take a program and quote it. Over here, it's kind of the opposite, taking a string and you are evaluating it. So you can have this representation of data and programs being kind of similar. So a lot of ideas basically were carried over from Lisp into JavaScript. But Netscape's browser wasn't the only one, and a lot of others came along, and all of these were competing with each other with their own implementations of their scripting languages. And this meant that there was a lot of difference in how applications would run on each browser. Sometimes you wouldn't be able to run one application on a certain browser. That happens nowadays as well, but standards like ECMAScript have enabled us to alleviate most of those problems. So now ECMAScript is a standard, and we kind of have a new version of the standard each year. But if you have a standard, it's not enough to use the language. You need an implementation, and an implementation is just a compiler. So in our case, it's Babel. The word Babel, well, I didn't want to admit, but I spent a lot of time just researching which way to pronounce it. Turns out that Babel is the more traditional way, and Babel is a more, American pronunciation of the word. So I just picked one and I stick with it. Babel has its origins in a story, a biblical story from the book of Genesis, from the Old Testament. So it's about a time after the Great Flood, when humankind, who at that time, according to the story, mythology, all spoke just one language, and they traveled to this land after the Great Flood and began to construct an almost infinitely tall tower which could reach heaven. And the gods were enraged by this, that humans were trying to reach some place that only the gods were allowed in, and confounded humans to not be able to speak the same language anymore. And that's kind of an origin story of how the languages are born. But Babel as a word and a concept has percolated into computer science and language theory, language design, so much so that even a compiler is named after it. And probably one of the most cleverly designed and useful compilers in our age. Now, Babel, the compiler, is a source-to-source compiler. So it takes in JavaScript from one end and spits out JavaScript from the other. So here's an example that I've taken from Babel's homepage. I just nicked it from there. But as you can see on the left side, you have one way of describing how you can map over a list to get another list with squares of the numbers in the first list. The left side is what we are giving to Babel to be compiled into what ends up being the right side. And as you can see, the left side is a little clearer. In other words, it's easier to see what's going on. For example, this little operator here describes exponentiation. So you're squaring the number. On the right side, it isn't so clear what's happening. In fact, you can see that there's this function that squares the number. And what we're doing on this side is kind of exposing an API, an underlying API. So the left side, you could say, is more elegant in that you can see things more clearly. It's also more abstract because it's not exposing what functions are actually, evaluating this operation. Babel is a compiler, and compilers are no longer monolithic, and they operate in stages, 4 stages more or less, which we'll go through one by one. The first stage is lexical analysis, which is also called tokenization. And that involves taking a program, and the English equivalent would be to look at a sentence and identify all of the words by seeing where the spaces are and where the punctuation marks are, and identifying the individual words in that sentence. So in JavaScript, you start with a program, you feed it to the tokenizer, and that gives you an array of tokens. Forgive my pseudocode here, it's not exact, but gets the point across. So after lexical analysis, we go to another stage called syntactic analysis, which is one of the more advanced stages in the compilation pipeline. And you take the output of the tokenizer, an array of tokens, and you compose an abstract syntax tree with it, which is just a tree representation of the entire program that you've written. And in JavaScript, because objects have an inherent tree-like structure to them, we can just represent one of these ASTs as a tree, and that's what Babel does. After that, we move on to a stage called transformation, which you won't usually find. The term transformation, you won't usually find that in traditional compilation, textbooks about compilers. This is more to do with the fact that Babel is a source-to-source compiler, because it's taking JavaScript and transforming it into a different form of JavaScript. And so it takes one abstract syntax tree, performs some mutations, some modifications on it, and that gives us a new AST, which then has to be fed to this thing called the generator, which creates a JavaScript string that can be nicely packaged in a file. There's a couple of other terms that we need to know. The traverser, which is this thing that's fed to the transformer, which walks the AST. What that means is it goes through the AST in depth first order, and it is invoked by the transformer, which ends up making the traverser walk the AST. And we have this thing called a visitor, which is an object that's passed to the traverser. And the visitor is just a description of what's supposed to happen when you reach a particular node in the AST. And that's what we'll really have to know in order to define these things called plugins, which help us to extend Babel. Here's a little piece of code that isn't actual code, but kind of describes what the transformer looks like. It takes an AST, defines a visitor, the visitor being an object that has properties for each of the kinds of nodes you'll be visiting inside the AST. So you might have things like identifiers or binary expressions, and the visitor describes what the transformation is supposed to be when you are both entering and exiting. But by default, it's just what happens when you enter a node. And the traverser then returns, after taking the original AST and the visitor, returns a new AST, which is the result of the transformation. And as I said before, Babel is a compiler that was designed specifically to be extensible with plugins. And there's two kinds of plugins, one for syntax and one for transformations. Syntax plugins being extensions to the parser component of Babel, and transform plugins helping the transformer do its thing. And each transform plugin implicitly invokes the corresponding syntax plugin. So I think this is a good time to just jump into a little project that I prepared, which will help us to understand how Babel works. So I've just set up an empty project and we can install Babel as a dependency. We'll be installing two things. The first is Babel core, which is the compiler and the command line interface, which will be used for our build script. And when we do that, we'll just prepare a little build script here. Which takes the contents of our source directory, which we haven't made yet. So I'll just make that. And outputs the transformed code into a light directory. So I'll just write a small function here so that we can see what Babel does. Let's call it double, which takes a number and returns 2 times that number. And that's it. It's taking some time to install. Once we're done, we'll run the build script and see what the output looks like. So I'll just run build script and that should, oh, sorry. And that creates a new directory that contains the transform code, or at least it was supposed to be transformed. But as you can see, it hasn't really done anything because Babel on its own is a compiler that doesn't do anything unless it's told to do so. And the way we do that is to use the corresponding plugins. If you need to use a bunch of plugins together, you use something called a preset, which is a collection of plugins. And just for the purpose of demonstration, I'm going to use a plugin called preset ES 2015, which takes ES6 code and compiles that down to ES5. So let's just install that as well. Now, installing that as a dependency isn't enough. You also need a configuration file. It's just good practice. You can also directly pass the plugins as parameters into the build script. But what we'll do is we'll define this configuration file that has a presets object. And inside that, we'll use the preset ES 2015. I think I've given the wrong package name, so I'll just. We're using Babel 7 in this case, and it's slightly different in its naming conventions from Babel 7, Babel 6. You also see a little warning that says that we should use Babel preset ENV instead of ES 2015. ENV is a slightly more sophisticated preset that allows you to define exactly which environment you're targeting. having some errors here. Can one of the more experienced people help me out in this case? I'm not using React in this case. Actually, I tried this before and it did work, but right, inside the Babel RC, in Babel 7, you have to use a slightly different name. That should work now. What was that again? No, but just a second. I'll just use this. Should have done that before. Anyway, I think what we'll do is we'll just use their REPL and if we use the correct preset, in this case yes 2015, we can take a function and compile it into something else. As you can see, the ES6 syntax on the left has been compiled into an ES5 syntax. So this way we can use plugins for extending JavaScript. There's a particular plugin that I actually wanted to show you, but since I can't get things working, I think we'll move on to macros, which is a subject that again comes from Lisp, but is quite obscure and hasn't been used that much in many other languages, but has sort of seen a resurgence in languages like Rust and Julia. And in JavaScript, the way you use macros is with either with a library or with extensions to Babel. And just to get acquainted with what macros are, they're these constructs that parse and transform code around them, and they're evaluated at compile time. So an example of this would be Sweet.js, which is a library, a compiler for macros. And this is a separate empty project in which I'm going to set up a very simple build script that will help us to see what Sweet.js can actually do. I'm going to install it as a dependency. Sweet.js itself is a compiler, and it takes code that contains macros and transforms it into normal JavaScript and uses Babel as a backend. But it's kind of an outdated compiler, and its community is sort of waning, hasn't seen too much activity in the past few years. But what it allows us to do is to create constructs that aren't present in normal JavaScript. So for example, we can define things like operators Let's say I want an operator that looks like this, is left associative. Sorry about that. And has a precedence of 1. Macros are in SweetJS just functions. So our operator is going to take a left-hand side and a right-hand side, and will return just this little piece of code that is the right side applied to the left side. Now we can see what this does when we compile it. Now, SweetJS itself uses Babel as a backend, but we'll be using Babel 6 in this case. There's a lot of other things you can do with SweetJS, and macros are quite useful in that they can be used to transform code at compile time without actually having to interfere with the compiler. And operators are just one of the things that you can do. That creates this little compiled file that doesn't contain anything. I don't know what that is. Okay, it doesn't seem to be working. Maybe we can just something's wrong. What I wanted to show you was creating an operator that looks like this, so that when you actually compile it using the SweetJS compiler, that converts the macro or any usage of the macro into JavaScript that actually can be run in say a browser or on Node. So what we have here is an operator that's similar to the JavaScript pipeline operator that takes it can take any input and pass it through, pipe it through a bunch of other functions. So in this case, we're trying to take 10, then double it, and then increment it. So you can see that the compiled version is just applying each of those functions from right to left instead of left to right. And of course, since Babel is so extensible, there's also a plugin that's called Babel plugin macros, which allows you to use macros with Babel, but the use case here is slightly different. Since we know that macros transform code and they extend a compiler, they're quite useful in frameworks like Create React App that are quite restrictive in terms of how much configuration they allow. Normally, if you wanted to, configure something in a project that used Create React App, you'd have to eject it out and then work with the Webpack scripts and such. But if you're using macros and if the particular version of Create React App or whatever you're using uh, is compatible with it, then you can do things like use those macros to transform code without having to uh, work with the actual Webpack scripts or the actual Babel configuration. So what we see here is a macro called CSS to RN, which takes normal CSS and compiles that into a React Native style sheet. On the left hand side, you can see the input, and the macro actually transforms that into a style sheet, which we can then use. And there's plenty of reasons to use macros over plugins. The most obvious one is that they can be quite easy to write. As you saw in the case of the operator which I defined, it was quite small, but if you wanted to make a plugin, you would have to define a visitor which would be quite large, and you'd need to know a lot about the AST, and they can save you quite a lot of configuration. To just sum up, you can think of Babel as a very elegant and abstract piece of software. Elegant because it allows you to use it in, it's quite well compartmentalized, and you can see things in a more, well, how do I say it? It's abstract because it's well compartmentalized, and its various components can be extended quite easily. So you have good abstraction there. But Babel as a compiler isn't just impressive because of how well it parses JavaScript. It's also quite a good community. I found it quite easy to get into uh, plugins and things because of the documentation, which was really good. And along the way, I think we've seen quite a lot of things from other languages which can be used. And I just like to say that it pays off to keep an open mind and learn from other languages along the way. And what really makes JavaScript awesome is things like Babel and its community that surround it, which have taken a language which had a lot of nasty things about it and allowed us to build a community which is really strong and quite open-minded, in that it takes advancements and integrates them into the core ideas of JavaScript. Thanks, and take any questions if you have any.